In example 4, we want to evaluate by converting to polar coordinates here. So we see that square root of x squared plus y squared, that's going to be in polar coordinates, that's our r. And then dy dx, that's our dA, that is going to be r d theta. And then we have to figure out our polar limits of integration here. So, well, our y limits of integration, let's go ahead and sketch our region of integration here. So are going from y equals negative square root 9 minus x squared to y equals 0. So, well, if y is the negative square root 9 minus x squared, then square both sides, and you get y squared is equal to 9 minus x squared. And then bring that negative x squared over as a positive. X squared plus y squared equals 9. So that's just a circle of radius 3. So our domain of integration is going to be inside this circle of radius 3. So it's x-axis and y-axis. Get our circle of radius 3 going here. And let's see. In rectangular coordinates, we're going from the negative square root, which is the bottom half of the circle, up to 0, which is the x-axis here. So we're going from the negative square root up to 0. And then we're letting that segment sweep here from 0 to 3. So x goes from 0 to 3. So x equals 0 would be right here. And then sweeping over to x equal 3 would be right there. So we're integrating over this lower right quadrant. So our domain of integration is right there. So how do we find our theta limits of integration? Well, we want to draw a general radial segment here. So here's a general radial segment. And we are going from r equals 0 out to the circle. And the equation of the circle here, well, if x squared plus y squared is r squared, so this is saying r squared equals 9, and then take square roots, r equals 3. So inner radius is 0, outer radius is 3. So that circle is r equals 3. So this will be integral, r is r squared of x squared plus y squared. dy dx is r d theta. That's our polar rectangular area. And then our r limits, 0 to 3. And then we let that segment sweep over the region. So here's at theta equals 0. Here is theta is negative pi over 2. So negative pi over 2 to 2 to 0. Or you could do, if you start here, 0, pi over 2, pi, 3 pi over 2 to 2 pi. Either one of those is fine. I'm going to go ahead and use the negative pi over 2 to 0. So r limits, theta limits. So now notice that this inside integral is completely dependent on r. That's independent of theta. So we can factor that out in front. So out in front, we've got integral 0 to 3, r times r there, r squared, dr. And then the theta integral is left, negative pi over 2 up to 0, and just d theta. So that's really 1 d theta. So we got two completely separate integrals. Well, this one's not bad. This antiderivative is just going to be r cubed over 3. And we're evaluating from 0 to 3. And this antiderivative will just be theta. And we are evaluating from negative pi over 2 to 0. So if we plug our 3 in there, 3 cubed is 27, divided by 3 is 9, minus 0 cubed over 3, so it's just 9 minus 0, 9. And then let's see here, plug in 0, negative pi over 2, and subtract. So that'll be 0 minus negative pi over 2. So this is just going to be 9. Double negative here is going to make a positive 9 times pi over 2. So 9 pi over 2. And we got it. So that one went quick. And then I'll just mention that there are some problems where they want you to sketch the solid that you're finding the volume of. So for us, our domain of integration is that quarter, and then our solid is going to be the volume under z equals r, which is a cone. So if we sketch the solid that we were finding the volume of that has volume 9 pi over 2 in xyz space, that would look like this. So here's y-axis, z-axis, x-axis. So let's see, y, x, z, and then this circle is in the xy plane, circle of radius 3. So that's down here in the xy plane. So this is 3 here, and then 3 here on the x-axis. And we want x positive and y negative. So x is positive, y is negative, so that's this region here. So the yellow, if I go ahead and dump in paint, this yellow region is right there. And we want the volume underneath the cone. So z equals r is a cone. So z equals, whoops, get back to blue here. Z equals r is our function, which is square root of x squared plus y squared. And if you look on your quadratic surface sheet, you square both sides, z squared equals x squared plus y squared. That's a cone, and it's along the z-axis here. And in quadratic surfaces, it would be written as x squared plus y squared minus z squared equals 0. And the a, b, and c underneath are all 1. So that's a 45-degree cone, and so that's going to look like this. And then we want the volume underneath that, but just above this quarter circle. So let's see here. We are going to have quarter there, and then also one here, and then right there. So we want the volume that's underneath that. So let's see if I can dump some color in here. So I'll do some green here. So it's underneath that cone. Let's see. No, this is kind of hard to visualize. I'm wondering, do I need those? I would keep this in and this. Let's see. Oh, yeah. There's also going to be a line right here, right? And yeah, so we want underneath this curved edge and below there, below here. So, well, yeah, that's not the easiest to draw. Would maybe been a little bit easier to draw if it was this quadrant out here. But hopefully you can visualize the volume underneath the cone above this quarter circle.